This is a summary of electric potential. We start by looking at ski lift. What does a ski lift do? So ski lift give a person the ability to slide down. So the ability to do work such as sliding down is what we call potential energy. So let's introduce potential energy. First, let's have a real quick review. In the mechanics, we have learned gravitational potential energy. That's the energy an object has when it has a different height. Of course, every object always has a height, a certain height relative to a reference point. So for example, a waterfall, the water can flow down because it starts from a higher potential energy and then it flows down to a lower potential energy. In this process, the potential energy is turned into kinetic energy. So another example is trap and escape. Using potential energy, it helps us to understand how objects stay on Earth. As a matter of fact, the potential energy between an object and the Earth is a negative value. And the potential energy at infinity is zero because objects always moves from a higher potential energy to a lower potential energy naturally. So if an object is on Earth, it'll remain on Earth. If we jump up, we'll go back on because every object tends to go to a lower energy naturally. So that's what we call trap, or say we call it secured. We're secured on the surface of the Earth so we don't fall off. On the other hand, if we have a space shuttle and we want the space shuttle to fly out of the range, what do? We need to give it enough kinetic energy so that the total energy will be at least zero for it to be able to fly to infinity. That is, if we say the space shuttle just start with energy. As a matter of fact, the space shuttle carries fuels, so it keeps adding potential kinetic energy to escape the trap of the potential energy. So the total amount of kinetic energy it has to gain in order to escape from the gravitational field of the Earth equals to the equation as we've shown here. That's the gravitational constant G times the mass of Earth and the mass of the space shuttle divided by R. Remember, it's R here, so it's different than Coulomb's law. It's not an R square. Electric potential energy is very similar in form as the gravitational potential energy. So outside a point charge Q0, which we call the source, the potential energy of a probe charge little q is 1 over 4 pi epsilon 0 q times q0 over r. And again, here's an r, not r squared. So this is different than Coulomb's law. And epsilon is the vacuum permittivity constant, as we introduced earlier, is one of the two constants that together define the speed of light. So is this a trap? Yes, this acts very similarly when we consider the conservation of energy. Infinity, when two charged particles are infinitely separated, the potential energy is zero. So here, there are three different scenarios. If both charges are positive, then this potential energy is positive. And then this potential energy will push the two charges away from each other until they reach infinity. When they are both negative, the potential energy is also positive, and two negative charges also push each other. The potential energy will keep decrease until it becomes zero at infinity. The third scenario is when the potential energy is made up of two charges, one positive and one negative. In that case, the potential energy is negative. Whenever the potential energy is negative, that forms a trap, which means either particle needs to gain kinetic energy as much as the magnitude of this potential energy value in order to gain enough kinetic energy at infinity, so that at infinity it can be at rest. So that is what we call a trap. So let's use an example to illustrate what trap and escape mean in the scenario of electric charges. So how much energy does it take to separate a proton from an electron in a hydrogen atom? Assume we can use what we learned. So first we read this and read this and read this, and we realize there's not many numbers given. How much energy means, so we're looking for kinetic energy. Separation means R equals to infinity. So if we do research, then we see potential energy plus kinetic energy equals to at infinity. All we need is to reach at infinity. So we need a minimum of 0 kinetic energy, and we know the potential energy is 0. That's why it's 0 plus 0. Okay, so if we do research about these constants, the mass of a proton, the mass of electron, and the separation between electron and the proton, and the R is approximate value. So we use the equivalence of the size of an atom, which is 1 angstrom. That's 1 times 10 to the negative 10th meters. So the given values are electron and the proton's charges, which is elementary charge in the unit of coulombs. Apply conservation of energy, then we can calculate the kinetic energy, and the numerical value is this. To answer it in a complete sentence, it takes a minimum of this much energy. What happens if there's more than, if the kinetic energy is more than the minimum here, then it will still have some kinetic energy when they're separated at infinity. Electric potential. This is the second part of the course. The first part, we introduced electric potential energy. The second part, we introduced a measurable concept. This can be measured. For example, like the wall sockets, they provide what we call a voltage that's derived from electric potential. So this is a very measurable concept. By definition, we define potential as the potential energy of a probe charge divided by the charge of this probe. So therefore, the potential belongs to the existing field independent of the probe. So if we use a diagram to illustrate the relationship between electric field that we introduced in the previous 2 chapters and electric potential, here it is. The electric field always points from higher potential to lower potential, and it represents the steepest descent path. Potential and field relationship can be expressed in calculus. So here is a multivariable partial differentiation. We know that the potential difference is the same as integration of electric field along the path. And in the meanwhile, electric field is the partial derivative of electric potential with respect to a particular direction. In this case, electric field is a 3-dimensional vector and the electric potential is a scalar. Therefore, we have 3 equations for the electric field along x, y, and z directions. Very interestingly, most of the time when we learn calculus, we learn all these analytical methods of doing the differentiation. With the advance of modern computing technology and the power of computing, more and more actual calculations are carried out using numerical methods. So for example, if we have electric field between 2 points along the x direction, without knowing the analytical equation, we don't have to know whether it's a sine function, it's a polynomial, or whether it's any other hyperbolic function. We don't need to know it, but as long as we know the 2 numerical values at V2 and V1, we can calculate the numerical derivative. That is E of x equals to the slope, V2 minus V1, divided by the distance between the 2 points, x2 minus x1. So the electric field between 2 points along y direction is similarly defined as the potential difference between those 2 points, only the numerical values. It does not have to fit in any of the analytical functions as we learned, such as polynomial. It doesn't have to be polynomial, it doesn't have to be a sine function, doesn't have to be a hyperbolic function. Then divided by the distance between these 2 points along the y direction. So that's y2 minus y1. We call this a numerical calculation because we only need to know the numerical value of this vast field at point 1 and point 2. That's how we can use numerical method to calculate electricity. We're going to do this in an experiment after this lecture. So here is an example of the simplest case. If you have two large thin metal plates that are parallel and close to each other, that's the definition of parallel plate. On their interfaces, the plates have excessive surface charge, density of opposite signs, and magnitude of this much of coulombs per meter square. What is the electric field between them? Okay, so this is a problem that actually involves what we learned previously. It's not just electric potential. So this is an example of what we call a complicated problem. So if we're going to read and read and read it, and we see, given a surface charge density, what's the electric field? And here is another reminder. Now we learned how to calculate electric field from electric potential. But let's just go out of this scope a little bit and go out of this box. We still solve problems using all the accumulated knowledge and skills, like what we said, is what's in our toolbox. So which concept of law is directly applicable to this? Although we just introduced electric potential, however, if you notice, what's given is the surface charge density. So we're going to use the equation for a electric field near a charged surface. Okay, because it says on their interfaces, the plates has excessive surface charge, and there's nothing on the outer surfaces, so the electric field goes out one direction. So we use the equation number 6 instead of 5 if you go back to review the previous summary. So if we apply the equation, then using the math, we can calculate that the electric field is 7.9 times 10 to the negative 11 newtons per coulomb. Okay, so to answer this, the uniform electric field between them is 7.9 times 10 to the negative 11 Newton per coulomb. And the direction, this is what we learned today. Direction is perpendicular to the two plates. This example shows us when we solve problems, we need to go out of the box to select what in the toolbox helps us instead of immediately what we have on the top of our mind. Okay, so the next example, we're going to make sure we use what we learned today. So two large thin metal plates is the same exact scenario, right? So here it's asking what's the potential between the two plates that are 0.10 meters apart. So this is a hypothetical scenario. Usually parallel plates are not so large. I mean, actually there are parallel plates that are large like this, but this is not a particularly typical case. But anyway, so let's use that 10 centimeter parallel plates. So if you read and read and read and you gathered what's given, and we can actually use the electric field as given because we just solved it in the previous problem. So this is, again, a complicated problem that involves multiple steps. So the unknown is the potential difference delta V. So if we use the definition, how the electric field is related to the electric potential difference, then we can apply for parallel plate delta V, the voltage or potential difference equals to the electric field E multiplied by the separation of the two parallel plates D. So delta V equals to electric field E times D. If we apply the math, and then we get the answer 7.9 times 10 to the negative 12 volts. And that's the potential between the two plates. In summary, we summarized 3 parts about the electric potential, starting from electric potential energy and how we can apply conservation of energy, definition of electric potential, and we introduced how electric potential is related to electric potential energy. Third, electric field as derivative of electric potential, that is the relationship between electric potential and electric field.